Hello, welcome to the second lecture of week 10. In the previous week, we had been discussing about some of the new niche areas of applications of nanomaterials. In this week, we are talking to you about the use of nanomaterials for energy applications. In the first lecture, I gave you an overview of the whole topic. We discussed the importance of integrating a storage technology with a energy generation unit to get a sustainable and secure energy landscape. We also introduced the importance and requirement of having efficient energy transmission strategies and devices which would fulfill the requirements of this application. We had been talking to you in the first lecture about the use of nanomaterials in these applications, that is primarily driven by the intrinsic advantage that is associated with the nanomaterials. The advantage is high specific surface area or high surface to volume ratio. So, applications where interfacial reactions or kinetics play important role will be dominated by the use of nanomaterials in them. So, in today's lecture, let us start with a technology that is impacting our lives tremendously in today's life, and that is the secondary batteries. So, in this lecture, we would cover the concept of a battery. I had introduced very briefly the concepts of primary and secondary batteries in the previous lecture, but we will give you clear differences or similarities between these batteries in today's lecture. You must understand the components that actually define efficient fabrication or the architecture of a secondary battery. So, we will discuss about the components required to fabricate a battery. If you look into a battery, it is linked with two concepts, namely the charging process and second the discharging process. Clearly, these two processes are different. What happens in these processes? Are they very different or they are similar to certain extent, but the way they occur inside the battery differentiates the place at which this is happening. This is defined by the working of a battery, which we will discuss today. Now, if you look into today's literature, various books articles, news articles, technological surveys or reports, you will find that large number of batteries are being reported, various types of batteries are being reported, while these batteries have different response characteristics or even they have a different nomenclature. For example, if you have a lithium ion battery, LIBs, or you have a sodium ion battery, the SIBs, then you will find clearly there is some difference in them. What is that? The difference comes from the materials used to fabricate these batteries. So, we will talk about the materials used to fabricate these batteries, and finally, the parameters which define the performance of these batteries, and you will see how those parameters are impacted by the use of nanomaterials, and therefore, you will be able to correlate the concept, that is use of nanomaterials in secondary batteries. So, a battery is an electrochemical device that converts chemical energy into electrical energy. It is made up of two electrodes, anode and cathode, and has an electrolytic solution. These electrodes are dipped in the solution of the electrolyte, and you have been seeing or using various types of batteries for different applications. On the basis of the reversibility and the electrochemical reactions that are observed in such batteries, they are classified into two broad subheadings. They are primary batteries or cells, secondary cells or secondary batteries. Primary cells are those cells which are non-rechargeable. So, they will be charged once, you will use them, and once the battery gets discharged, you will discard the batteries, or you will replace the batteries with a new primary battery. Here you will find that the reactions which take place are irreversible chemical reactions, and you have been using such batteries in remotes, watches, clocks, and many other applications, and the typical examples are dry cells or zinc air batteries. In comparison, the secondary cells are rechargeable, meaning that you can use them multiple times by repeated charging and discharging. Here the chemical reactions which take place are reversible in nature, and you are seeing you use them in inverters, automobiles, large number of phones, mobile technologies, laptops, wearable electronics and many other places, and you have been seeing them as lead acid, lithium ion batteries, sodium ion batteries, nickel metal hydrides, nickel cadmium and so on so forth. So, if you look into the primary battery, you will find that they are mostly dry cells. So, they are not using any electrolyte which is fluidic. So, you will have an architecture which is given in this figure. So, you have various materials that drive the reactions. For example, at anode for a zinc carbon battery, you have zinc which transforms to zinc 2 plus, giving away 2 electrons. At cathode, you have these electrons giving out ammonia and hydrogen. This ammonia reacts with zinc 2 plus, giving ZnNH3 twice, and hydrogen reacts with manganese oxide to give you Mn2O3 plus water, and overall the reaction is written here. So, you find that you have a flow of electron from one end to the other, and that gives you the current. In secondary batteries, for example, one of the most used batteries, let us say in a lead acid battery, you have an architecture which has large number of cells attached together to give you a battery, and you have lead plates and electrolyte filled in between, and then you have the cell connections and the terminal posts which are put inside a cover. So, at anode you get electrons that react with SO4 2 minus coming from the dilute H2SO4, which is acting as the electrolyte in this system, and you get lead sulphate. While at cathode, what happens? The electrons which are released, they react with lead oxide plus the H plus ions coming in from the acidic electrolyte, and you get water plus Pb2 plus, and overall then you get the reaction where the electrons move from the anode side to the cathode side, and you get electricity. And if you reverse the reaction or desulphate, then you get back lead oxide and you can recharge the batteries n number of times, because the reactions are reversible. If you look into a lithium ion battery, you will find it has components which are anode, separator, electrolyte and cathode, where anode and cathode are coated on current collectors. So, behind them there is a layer of current collector which facilitate the injection of electron or acceptance of electrons from the anode or to the anode during discharging or charging cycles respectively. So, if you look into the anode, it is the negative electrode in a battery where oxidation occurs, while separator is a permeable membrane that prevents the electrical contact between the two electrodes while allowing the ions to pass through. Electrolyte facilitates the movement of ions between the electrodes, and cathode is the positive electrode in the battery where reduction occurs. So, if you look into a battery, what is happening during a charging process? You have from, for example, lithium cobalt oxide, you have lithium coming out and going and getting intercalated inside the anode, that is the layered graphitic like structures. While discharging, the ions go back and the electrons which were injected during the charging process in the anode to maintain the state of charge neutrality, then come out and pass through the external circuit to give you the current. So, anode undergo reduction while cathodes go through the process of oxidation, and the electrical energy is converted into the chemical energy and stored inside the electrode material in such batteries, and then when you require them, then the chemical energy is converted to electrical energy. So, these batteries have the requirement of redox reactions, and that is a typical way the charging or discharging process takes place. So, you have the electrons flowing through the external circuit to power the device, where the anode now undergoes oxidation and releases electrons, while cathode undergoes reduction by accepting electrons. So, what happens here? The chemical energy converts to the form of electrical energy that flows through the external circuit. So, during charging, one electrode acts at the place where oxidation takes place and the other acts as the place where reduction takes place, and their roles are reversed during the discharging process. During charging, you are giving electricity so as to maintain the charge neutrality conditions at both the electrodes, while discharging, the electrons are flowing through one of the electrodes and coming back to the other electrode, that is from anode they flow back to cathodes through an external circuit, because internally that flow is not allowed because there is a permeable membrane. So, that both the sides are charge neutral, and that is giving you the electrical energy flowing through the external load. So, you have cathodes, electrolytes, anodes and separator. Now, when you use nanomaterials, then you have these materials which can give you high surface area that in turn increases the number of active sites where these redox reactions can take place, and higher is the number of redox reactions taking place, higher is the energy storage capacity. You can tune the flow and storage capacity of the ions, and hence you can tune ionic conductivity, as well as by tuning the structure, the nano size structure of the materials, you can also tune their electrical conductivity by modulating their confinement as well as band gaps. As we know, nanomaterials are structurally stable, they can sustain high mechanical stress. Hence, what do you get? You get better structural stability. So, if you look into the materials which are used to fabricate these batteries, what do you get? You have cathodes, you have electrolyte, anodes and separators. We know, and we have been seeing for last nearly 10 weeks, that nanomaterials have the intrinsic advantage of high surface area, which in turn gives you higher number of active sites where the redox reactions can take place. Now, you can have high ionic conductivity and electrical conductivity in these systems by changing their confinement and nature of confinement and the associated band diagram. We already know that these nanomaterials have high mechanical stability. So, you can have materials which are structurally stable. So, you can make batteries which are very stable. You can have lightweight batteries. You can have tunable morphologies of nanomaterials that will be used in these batteries. You can tune the material itself, you can tune the anode materials, the cathode materials, nature of separator, or you can even have electrolytes which are aqueous or non-aqueous electrolytes, and tune the porosity or ionic pathways in these electrolytes, and then you can modulate the storage capacities in these batteries. Once you do that, you can improve the cycle life while maintaining the mechanical integrity of the batteries. If you look around, you will find that, for example, there are various types of materials which are being used in structures other than lithium ion batteries. For example, V2O5 is extensively being used in aluminum ion batteries. Sodium iron phosphates and sodium titanates are being used in sodium ion batteries, and you can, just by looking at the crystal structure, the way they are forming, you can clearly see that they will have different pathways for the electrolyte ions to go through, or they will have different nature of ions which would be exposed on their surfaces for undergoing electrochemical reactions. Hence, you can change the reversible chemical behavior in them. You can have different charging and discharging mechanisms. You can have structures which are very stable. These crystal structures are very stable. So, you can have stable phases, that means the materials can remain stable for large number of electrochemical cycles, meaning that the batteries can undergo large number of charging and discharging cycle. That means, you can have high lifespan for these batteries, and you already know the other advantages in terms of weight, capacities, higher electrical and ionic conductivities. They are able to sustain the volume change during charging or at higher temperatures because of the capacity to have the mechanical stress absorption, and therefore, you can have very stable batteries. You can have not just conventional layer type graphitic structures which were allowing the charges to go inside and get trapped, and that means you had the storage capacities. You can tune these materials as per as the requirement of the end user. So, you can have graphene oxides, you can have carbon nanofibers, or you can even have hollow carbon structures which have different orders of confinement, different specific energy densities, and therefore, they have different capacities to store charge. Each one of them also have a different carbon footprint of their own. So, sometimes you will find that it is not always true that the best performing materials would be used in industries. The reason is that high performing materials can also have slightly complicated synthesis protocols which can increase their carbon footprint. So, you need to go to simpler materials which give you the advantage of weight, you get high densities without compromising the chemical reactions or thermal or electrochemical stability, and then those will be used by industries. So, these are some of the high end carbon structures which are being used in next generation batteries, and you can clearly see that their shapes and sizes are different, and therefore, their response characteristics would also be very different. You can have electrolytes which are different. You can have aqueous electrolytes or you can have non-aqueous electrolytes. As you move from one electrolyte to the other, some may have higher ionic conductivity, but their temperature stability may be lower. Some may have higher ionic conductivity, high temperature stability, but their cost may be very high. Some may have medium ionic conductivity, but very low cost, and various combinations. So, depending upon the requirement of the batteries and the economics associated with those batteries and applications, you will have to choose the right electrolyte, because the electrolyte is one of the most expensive components in a battery. You can have various types of electrolytes. You can have liquid electrolytes, you can have organic electrolytes, you can have ionic liquid based electrolytes, solid polymer, gel polymer, or you can have solid crystalline electrolytes. Each have their own advantages and limitations. It is not that there is one perfect electrolyte. So, you have to be very careful in choosing the electrolyte for making a battery, because the performance of the battery is strongly dependent on the characteristics of electrolyte, but you should also keep other parameters in mind while you choose the battery electrolytes. Then you can have separators, you can see that there are various parameters which you need to be choosing before you decide the separator which you will use. First of them is that separator should have the property that it should not take part in the electrochemical reaction itself, but it should have the capacity to prevent electron flow through it while allowing pathways for ion transport. It should be chemically stable, thermally stable as well as mechanically stable. Typical parameters you look at when you are deciding a separator is that their thicknesses are generally less than 25 microns, the pore size is less than 1 micrometer, porosity is 40%, electrical resistance is 2 ohm per centimeter square, and they can sustain high temperatures while having reasonably high melting temperatures. There are large number of, again as we have been discussing in the previous examples, there are large number of materials which can be used, fabricated, and therefore, you can get different types of batteries. So, nowadays you can get in the market some batteries which will operate till 3 volts, some will operate till 2 volts, some will operate up to 5 volts, some have different energy densities, some have low cycle life, some have high cycle life, some are more expensive than the other. Now, you will be able to understand it is primarily driven by the combination of materials which are inside, because if you change the material, then the cost will surely change, but also all the response characteristics will also change. Hence, if you have a certain requirement of energy and power density in a given system, please choose the battery which gives you the ratings as per as your requirement, because that can only be fulfilled by a certain set of combinations of cathode, anode, electrolyte and separator. Some of the commonly used materials for cathodes are lithium cobalt oxide, lithium iron phosphate, lithium nickel oxide, or lithium nickel manganese cobalt oxide, and so on and so forth. You have different types of carbon and nanocarbon alloys which are being used as anode materials. You have various electrolytes, and similarly you have various separators. If you look into the specification sheet of the batteries, they will give you the value of theoretical energy or capacity. This is given by the value half C V square, where V is the operating voltage window. Theoretical voltage V is the ideal operating voltage window of the device which comes out from the redox potential, and associated to that the theoretical capacity in terms of the active substance which is being used, which is the material taking part in the overall electrochemical reaction, is given by I delta T by delta V, and efficiency is given by energy retrieved from the storage device during discharge to that of charging into 100. So, now you know that you can change the voltage window of a material by changing its size, because then their band diagrams can change. You can modulate the redox reaction in various materials, again by changing the surface to volume ratio, and as you change the band diagram, the current which you can obtain would also change, and those will directly impact the efficiency, the capacities and the energy densities which you can get from such storage devices. So, next time when you look into a battery, please be careful. It is not a very simple, trivial device. It is a much more complicated and a non-trivial device, which is comprising of large number of components, which would have different responses to various parameters that can change around it, for example, temperature, pressure, magnetic field or even electric field. So, you must manage the batteries very carefully if you want to obtain the desired output from them, and if you want to make new battery systems, new battery technologies, you have to make new materials, understand their electrochemical response behavior, and subsequently you will be able to bring them together to make new batteries, and that is what is happening. It is not always the limitation of the source. For example, we always say that lithium ion batteries, you want to make new batteries other than lithium ion batteries, because the source of lithium is limited. Along with that, you also have requirements like stationary applications, where other batteries such as sodium ion batteries, which can become extremely useful in comparison to lithium ion batteries, because sodium batteries can go up to 0 charge and they can be brought back easily. But if you take lithium ion batteries to a state of deep discharge, then they cannot be revived easily. You have to pump in lot of energy, and when you do so, you degrade the materials, and hence the cycle life of the material comes down, and the overall lifespan of the battery then is significantly reduced. You should not use the batteries in an very uncontrolled manner, because then you are directly impacting the materials, and hence you will lose the battery performance. If you can have a controlled utilization of these battery systems, then you will always find that the efficiencies of the devices which are taking energy out of these batteries would also remain very high. Sometimes we remain ignorant about these facts, and hence the performance of the device comes down. But now, after this lecture, I am pretty sure that you will be very careful when you use the batteries, and you will find that you will be able to efficiently use the energy storage devices which are based on such batteries. You will be able to then find, using techniques like CV and CD, the values of the specific capacitances that are there, and you will be able to get the specific power, specific energy densities and cycle life from these batteries. So, if you perform a cyclic voltammetric measurements or charge discharge measurement, then these are the two formulas used to determine the specific capacitances, which we will discuss in the week where we are going to talk about the characterization tools used to fabricate or characterize these batteries. Hopefully, now it is clear that the energy storage technologies can be of two types, primary or secondary, and secondary batteries, which we are tremendously dependent upon in today's world, are non-trivial devices. They have extensive use of nanomaterials, and as we improve on the performance of these nanomaterials or we make newer novel nanomaterials, new battery technologies will evolve with time and they will find large scale commercial usage. These are some of the references which would be very useful to develop even more understanding about the topics that were covered today, and I thank you for attending the second lecture of week 10. Thank you very much.